We're going to talk a little bit about structure and properties. In particular, we're going to talk about how structure affects electronic properties of molecules. So we'll review ionic and covalent bonds. We'll introduce polar covalent and nonpolar covalent bonds again. We'll define bond polarity and dipole moment, and we'll learn how to represent both bond polarity and dipole moment on molecules. And finally, we will learn how structure affects dipole moment. So let's review a little bit. Ionic bonds are between a metal and a nonmetal. In these bonds, electrons are transferred within the bond from one element to the other. The positive side is called the cation and the negative side is called the anion. In sodium chloride, the sodium is the cation, the chlorine is the anion. By convention, we write the cation first and the anion second. If you feel that you have trouble remembering which word goes with which charge, cations have pause. Ionic bonds are the same in all directions, which means they're isotropic. They form extended ordered structures called crystals, which have a repeating arrangement of atoms in 3 dimensions. There is an enthalpy associated with this type of bond forming, and that is called the lattice energy. Okay, so this is where we extend our information about ionic bonds. The strength of an ionic bond is called the lattice energy. Recall that covalent bonds is one in which the electrons are shared between the 2 atoms in the bond. They can be perfectly shared, in which case we call them nonpolar covalent bonds or pure covalent bonds, as our book does, or they can be unevenly shared, and we call them polar covalent bonds. We represent a partial charge using a lowercase Greek delta with a plus or minus sign to indicate the partial charge on the molecule. So in general, we accept the threshold for nonpolar covalent bond as an electronegativity difference of less than 0.4. An electronegativity difference between 0.4 and 1.8 is generally considered covalent. And if you have greater than 1.8 for your electronegativity difference, it's considered an ionic bond. But in the end, this is all a spectrum, so we end up talking about the covalent or ionic nature of the bond and which one it acts more like. So we're somewhere in the middle. All right, now something we haven't actually talked about before, but which we should address, which is also in the book, is that covalent bonds form when you overlap orbitals. So the bond distance in a covalent bond is given by the lowest potential energy on a graph like this to the right. So this is a energy versus internuclear distance. And so we're bringing 2 atoms together. They're forming a bond when their orbitals overlap. And if we put them too close together, their nuclei start to repel each other. So on the left-hand side, where the energy is starting to go up toward infinity, that is where the nuclei are repelling each other. On the far right-hand side, where we show 2 separated balls, we have no overlap and therefore no bond. So we've got a sweet spot that is the covalent bond, where the energy is at its lowest point. And this is a common representation, which you will see many, many times again in the future if you continue taking chemistry courses. All right, moving on. When you represent bond polarity, so polarity meaning a separation of charge, you write an arrow with a line through the middle on the non-business end. So this is actually a vector. The arrow should point towards the more electronegative element in the bond pairing. So in water, this means that the arrow points towards the oxygen. As previously mentioned, we represent partial charge with lowercase Greek delta. So in this case, the hydrogens are partially positive and the oxygen is partially negative. So when we want to represent bond polarity, we figure out which element is more electronegative, and then we give it these funky little Greek deltas and an arrow to indicate the vector. So let's try this. Draw the bond polarity line for the following. So for each molecule, draw that polarity line and then put on the partial charge. So as a reminder, the electronegativity trend is upright. So the arrow direction will go toward the more electronegative element and the partial charge will go on, or the partial negative will be on that element. So in HCl, chlorine is more electronegative, so the bond polarity goes toward the chlorine, which puts the partial negative on chlorine and the partial positive on hydrogen. Okay, now SO2 actually forms a resonance structure with a trigonal pyramidal electron geometry. In this case, we have a lone pair hanging out and then a resonance between a double and single bond on those oxygens. We have a partial negative on both of the oxygens because oxygen is more electronegative than sulfur via our electronegativity trend, and sulfur has a partial positive. Okay, so then we look at chlorobromide, or actually bromochloride. And bromine is less electronegative than chlorine, so we point toward the chlorine. The partial negative goes on chlorine, the partial positive on bromine. And again, I'm just using the trend for upright as far as electronegativity is concerned. All right, so let's talk the difference between polar and nonpolar molecules. And in order to do that, we're going to use our electron geometries and molecular geometries. If the electron geometry from VSEPR is unequal to the molecular geometry, the molecule is polar, unless it becomes linear or square planar with only one outer atom element. So what do I mean by that? Basically everything where electron geometry is unequal to molecular geometry is polar, unless it perfectly balances. And we're going to talk more about that in a little bit. So basic geometries will apply when all outer atoms are the same element, when all domains are bonding domains, and when bonding domains are all single bonds. Anything other than that, and the electron geometry will not match the molecular geometry, and you will have a polar molecule unless it's linear or square planar. Okay, so let's talk a little bit more about what this means. So if you have polarity, it will have a dipole moment. Let's talk about what dipole moment is. A dipole moment is the sum of the bond polarity vectors in a molecule. I specifically use the word vector here because I am referring to a quantity with both magnitude and direction. Magnitude meaning how big, and direction meaning literally just direction. So if you add vectors of the same magnitude but opposite direction, together they equal 0. So let's take a look at carbon tetrachloride, chloride there on the left, CCl4. It has a tetrahedral electron and molecular geometry. So each one of these bonds has a bond polarity, and we can write the bond polarity down with those nice arrows. So those are our vectors. Because our electron geometry is equal to our molecular geometry, this is a perfectly balanced case. Everything is evenly spaced. By definition, that's what VSEPR predicts. So this has bond polarities that cancel out perfectly. They equal 0. Carbon tetrachloride is a non-polar molecule. Repeat, even though the bonds have polarity, all of them added together mean a dipole moment of 0. Now water, on the other hand, we know is one of the most polar substances out there. So how did this come to pass? It also has a tetrahedral geometry, but water ends up with a bent shape due to the 2 lone pairs on the oxygen atom. The lone pairs introduce asymmetry in one dimension. This results in the vectors not canceling out. They're additive instead. So we get a dipole moment represented here by lowercase Greek mu in the direction of the oxygen. If the electron geometry is unequal to the molecular geometry, the molecule is polar unless it is reduced to being linear or square planar with only one outer atom element. So to summarize, ionic bonds are between metals and nonmetals with electronegativity differences of greater than 1.8. They are the strongest bonds in which electrons are transferred, and we have a positive cation and a negative anion. They form crystalline structures with repeating 3D shapes. Covalent bonds are between 2 nonmetals. A pure or nonpolar covalent bond is perfectly equally shared electrons with an electronegativity difference of less than 0.4. So all heteronuclear diatomic compounds are pure covalent. In other words, like chlorine gas, hydrogen gas, etc. Polar covalent bonds are unevenly shared electrons. So they're somewhere in between being pure covalent and ionic. They have an electronegativity difference between 0.4 and 1.8, and they have a bond polarity pointing to the more electronegative element, and that is given by a vector line where you have a little arrow and you have a cross on the bottom of it. Okay, and finally, if the electron geometry is unequal to the molecular geometry, the molecule is polar, meaning it has a dipole moment, it has a separation of charge, unless it becomes square, planar, or linear with only one outer atom element. We will practice this. Don't worry, it takes some practice to get this down. But that summary statement in red at the bottom is very helpful to figuring things out.